Here we are for section 2.5, and here we start beginning the idea of what is called continuity. And really, continuity is very much just as it seems. When we have the graph, it's very easy to see. When we have the equation, it may require us to get the graph or something else. But realize continuity does play a big part in calculus, and the fact that if there is a discontinuity, we can actually remove it if necessary. And so that's what we're going to be looking at in this particular section. A discontinuity is any place where the graph either has a hole or it has a break. And so the first two questions here says find all points where the function is discontinuous. And in particular what it's asking for is at what values for x is this discontinuous. Well, if I look at number 1, I see there's a hole in the graph by that open point right there, right at -2. So I know -2, there is a discontinuity. Now as it turns out, this discontinuity is removable. We can remove it pretty easy since it's a hole. But but there is a discontinuity. Also, it's pretty obvious that when we see the hole for 2, there's a discontinuity there as well because it has a hole. But one that's not as obvious, well, it's actually more obvious, but it seems to be one that we actually forget, is where the break is in the graph, and the break occurs right at where x equals 0. Basically, we have an asymptote there, and so those would be the 3 places or the 3 points where it's discontinuous. Likewise on number 2. Now, the only place that appears to be a break, there doesn't appear to be any holes, is right at the point where x equals 3. We can see the symbol or those dashed lines representing an asymptote, and realize that asymptotes are naturally a break, and so they would become a discontinuity. Likewise, asymptotes are discontinuities that cannot be removed because there will always be some sort of a gap. Whereas if you have holes in them, then it is possible to remove that discontinuity. So that is the answer for the first 2 questions. The next group of problems, 3 and 4, asks us to answer the question, and we look at, or they give both the equation and the graph. Thankfully they give the graph because the graph is a whole lot easier, and it basically asks for number 3, does the limit as x approach 1 of f of x exist? Now remember, in order for this to be true, we have to look at both ways where x is equal to 1, and does it approach the same number? Well, as we go towards where x equals 1 from the left hand side, it appears to be going to the value of 2. If we look from the right side or from the positive side, it appears to be going to 2 as well. But notice that there's a hole right there at 2, or at when x equals 1. The question becomes, does the limit exist? And we've looked at it plenty of times to realize, yes, they are going to the same place. Just because we don't get there doesn't really mean anything. They are heading towards the same place. Likewise for number 4. The limit as x approaches 2 of f of x, does that equal f of 2? Well, let's see. The limit as x approaches 2. From the left hand side, it appears to be heading towards -4. From the right hand side, it appears to be heading for 1. And so what we could argue here is the limit doesn't even exist. So when we ask, does the limit equal f of 2, the answer has to be no, because the limit doesn't even exist. But we might be able to change this. Does the limit as x approaches 2 from the left equal f of 2. Well, that's a false statement because from the left it appears to be going to negative 4, but if we look carefully, f of 2 equals 0. And likewise, the limit as x approaches 2 from the right or from the positive side is 1, but f of 2 is 0. So neither one of them, neither one of the one-sided limits don't even equal that. Okay, the next group of problems. The directions say find the intervals on which the function is continuous. Basically what we have going on here is where are the asymptotes? Because if we have asymptotes, we know that they will cause a break. And once we get those breaks, then we can get continuity, or it will be continuous elsewhere. So we look at number 5. The denominator in this case is x squared minus 5x plus 6, and we need to find out where does that equal 0, because if it equals 0, this would become discontinuous because it's an asymptote. So we factor this out. This is x minus 3 and x minus 2, and set each one of these equal to 0, and it becomes simple algebra at this point. X equals 3 and x equals 2. Those would be the asymptotes. Otherwise, it should be continuous everywhere else. So how do we show this? Well, using interval notation, it's going to go from negative infinity all the way up to, but not including, 2, along with everything just above 2 up to 3, and then everything just above 3 to infinity. Now, realize you may have had this exact same answer last year, but instead of asking where is it continuous, we would have been asking what is the domain. And realize it's not the same question, but it would have ended up being the same answer. Example 6, we have y equals 3 cosine of theta over theta plus 6. Well, the only place we have to worry about discontinuities is when this equals 0. And that's pretty simple. Theta plus 6 equals 0, so that means theta equals negative 6 is the only discontinuity that we should have. So that's the only place it won't be continuous, and so we look at it's going to be from negative infinity all the way up to negative 6, but not including negative 6, and then we start just above negative 6 and go to infinity. The next group of problems asks us to find the limit and determine if it's continuous at that point being approached. So we need to use our methods of finding limits, and we're going to try with direct substitution and go from there if we can't. So the question is, what is the limit as x approaches 3 pi of the sine of 9 pi over 2 of cosine of the tangent of x? Now, really the big things we need to realize is sine is continuous everywhere. Cosine is continuous everywhere. Tangent has a slight problem. Tangent is discontinuous whenever cosine equals 0. So that's at pi over 2 and every multiple of pi thereafter. So we need to look at, we're approaching 3 pi, not 3 pi over 2. 3 pi over 2 we might have a problem because we wouldn't be able to directly substitute. So let's just substitute in and see what we get. This would equal sine of 9 pi over 2 times the cosine of the tangent of 3 pi. And we all are very good trig students because we remember that the tangent of 3 pi is equal to 0. And so this would be the sine of 9 pi times, cosine of 0. Once again, we are very good trig students, and we remember that as being 1. So this becomes the sine of 9 pi over 2, and sine of 9 pi over 2 is equal to 1. So the actual limit does exist, and then the question becomes, is it continuous? Well, as mentioned before, the only place we really have to be concerned with is when tangent is equal to pi over 2 or a multiple of pi after that. And that does not apply with the 3 pi. So yes, it is continuous at that point as well. Realize we may have come up with the value of 1, but it not be continuous. So we do need to be careful with that situation. Okay. And the final example we're going to do on this particular video is the last one in this group, and that's number 8. The limit as theta approaches negative 3 pi of the tangent of pi over 4 times cosine of the sine of theta. Okay, once again, we have to be concerned with, does this end up being, when it's approaching negative 3 pi, does this end up getting close to pi over 2 or a multiple of pi thereafter? And basically, that's what we're going to find out as we work this through. So let's try direct substitution. We get pi over 4 times the cosine of the sine of negative 3 pi, which will equal the tangent of pi over 4 times the cosine of, the sine of negative 3 pi is 0. And the cosine of 0 is 1. And then we finally get to do our test. Is this a defined value? And the answer is yes. Tangent of pi over 4 equals 1. Nowhere did we have any problems with discontinuities, and so we answer the second question, yes, it is continuous right at that point.